Perhaps you've seen this example before. A bicycle is pushed on a flat surface. It rolls forward and remains upright. This is a form of internal stability. This internal stability is kind of remarkable. Why doesn't it fall over? What's even more remarkable is that the bicycle exhibits external stability too. Watch what happens here when he disturbs the bicycle. You'll note that it returns to an upright position. The stability of the bicycle is not just a curiosity. Turns out if the bicycle wasn't stable, it would be very difficult, if not impossible, to ride. So now you've seen both internal and external stability in the real world. The question you might be asking yourself is, why does the bicycle have stability? It turns out that answering this question is not easy. Making a mathematical model of the bicycle is quite difficult. We can apply a little common sense to the problem. For example, if the bicycle is not moving, if it's still, we know it'll fall over right away, so it doesn't have stability when it has zero velocity. Immediately one thinks it has something to do with the spinning wheels. One thinks it might be gyroscopic, just like a toy top won't fall over. Turns out, this is a theory that you'll find a lot on the web, and it's false. We know that gyroscopics are not important to stability of the bicycle, since the mathematical model shows that they contribute very small terms to the stabilization. Some very clever experiments have shown this to be true as well. Here is a bicycle that's built with counter-rotating wheels, so as to cancel out any gyroscopic effects. Yet this bike is perfectly rideable and stable. So why is the bicycle stable? Well, it has to do with its characteristic values. Yes, those lambdas. And the lambda values are primarily dependent upon two variables. One is the speed, and the other is what is known as the trail, shown here. The trail is the distance between where the steering axis intersects the ground and the contact point of the bicycle wheel with the ground. A larger trail will make the bicycle more stable. In the figure here, the trail is positive. If the trail is negative, the bicycle will most likely be unstable. So the stability of a bicycle is very much dependent upon the geometry of a bicycle, and that's important. If gyroscopics were the main issue in stabilizing a bicycle, then rear wheel steering would work. Bicycles where the rear wheel is used for steering have been investigated for several decades. In fact, in the 1960s, there was a major project to make such a motorcycle, and this project failed after the expense of over $1 million. Fundamentally, these bicycles are very unstable and extremely difficult to ride. It's the characteristic values that make it so. Recently, after very careful mathematical modeling, a rear wheel steering bicycle was developed. This bicycle is rideable because of its geometry. Note that the seat is very high up, raising the rider's center of gravity. Furthermore, the rider's center of gravity is placed above the driving wheel. This bicycle is not stable, but it is rideable, and the reason why is because the instability of the bicycle is slow, and therefore the rider can counteract it.
Right, so stability, fact or fiction. We're going to make some example systems today and then determine the external or internal stability of them. So as a quick review, internal stability is stability with respect to initial conditions, and external stability is stability with respect to the input. So to start off, our first example is going to involve some calves that we have from a farm. So we're going to have a field, right? and then we're going to put a group of calves in the field. They're going to be chilling there, and that's going to be the system, that group of calves. Now the input into the system is going to be people, and when people walk up to the calves, the output will be the displacement of the calves from their origin. Okay, so in general, when people approach the cows in the system, the calves are going to walk away and be all skittish, right? That's how the system normally works because the calves are afraid of people. So when we're testing the system for its external stability, we're going to go and we're going to put a small input into the system, one cow whisper, and see how the cows react to that. So we see here one cow whisper DV walk into the system, and the calves stay very still. They stay still for a super long time, and eventually even like approached him a little. So system is externally stable. Right, so the next system we're going to do is going to be pretty much the same as the first. We're just going to use sheep this time. So system sheep, input people, output displacement. In normal use of the sheep system, when people are inputted, the sheep will rapidly run away and displace. So we tested this system for external stability the same way we tested the sheep system before. The big difference is that the sheep system is way more sensitive to input than the calf system was. So we had to combat this, and to do that we made sure that the input for testing for external stability was super small. However, the sheep still immediately scattered when the input was applied and when the person approached the sheep. So the system is definitely externally unstable. Chickens were the next animal on the list, and we put them in the same basic system as the last two. Now, the chickens stayed relatively still when left alone, and immediately ran away when approached by a person. We decided to test this system for internal stability. So, we took one chicken and changed its initial conditions and had 0 input put on it. We moved it away from the origin and waited. And, given a little bit of time, the chicken moved back to the origin and stayed there. This system is internally stable. The last two systems we show will be set up differently than the previous ones. For these, the system will be a cow, the input will be a push to the cow side, and the output will be the displacement of the cow. Now, if a great enough force is applied, the cow will move to the side, or, if applied quickly enough, it might even tip over. This system will be tested for external stability. The cow will start with 0 initial conditions, and we will approach the cow to apply a small force to its side. As you can see, this cow does not care about the input. This system is definitely externally stable. Now, we will perform the same test on a new cow and thus a new system. We will find the test for external stability to have quite different results on this new system. When the small force is applied, the cow has a large displacement away from the origin. This is an externally unstable system. Well, that's all. I hope this video has been at least somewhat helpful in understanding the general concept of stability.